Feeling good? Not too horrible? All right. Then we are going to continue right along. And the impression I've gotten, I think when I was going through Algebra 2, we didn't cover this, and so this was new to me by the time I hit pre-cal. The impression that I've gotten from a lot of people is that they actually have seen this before, but I'm still going to teach this as if this is something entirely brand new. And in fact, this is something that we are going to kind of develop and hone together. So we were looking at exponential functions last time. For that kind of previous section, we are going to create a new function. And the only condition that I really care about for this function is I want this function to be the inverse function for my exponential function. So exponential functions, these were our y is equal to a times b to the x. And I actually think that this a makes things a little bit tricky. And so we're going to look at a simplified version of this. We're just going to assume that a is equal to 1 here. All right, so we're just focusing on y equal to b to the power of x. And I want to construct the inverse function for this particular thing, for our exponential function. As far as our inverses are concerned, how do we find the inverse function of a thing, of anything, of an equation? We switch the x's and y's, and then normally what do we end up doing afterwards? We solve for y. We like to kind of get it into y equals something. So let's go ahead and let's swap the x's and the y's here. This is going to become x is equal to b to the power of y. And then I would just kind of like to note right away that it's actually pretty hard to now solve this for y. That is not going to be super trivial. We're going to need some new kind of machinery to be able to do this. But there is still some kind of meaningful stuff that we can talk about with what our new function is going to kind of look like before we rearrange things to make it so that our input is actually looking like an input and that our output is actually looking like an output. All right. So first and foremost, thinking back to my original exponential functions, what could I say about the domain of my exponential function? And what could I say about the range, given in this case that a is just equal to positive 1? What is our domain for all of our exponential functions? All real numbers, don't have to worry about anything. That's purely just a consequence of the fact that we let b be positive. We made b be positive, so we don't have to worry about dividing by 0. We don't have to worry about taking the square roots of negatives as well. And then if a is positive 1, what is our range going to be? 0 to infinite. Very, very good. So all those positive values. B raised to a power when b is positive, only ever going to be a positive. All right, awesome. Now, when we are taking the inverse function, what do I do with my domain and my range? We switch them. We swapped our x's and our y's. We switch our domain and our range. We switch our inputs and our outputs. All of that kind of stuff switches, and all of the kind of analogous terminology that goes along with that switches as well. And so what was the range of my original function is now going to become the domain of my new function. So the domain of my inverse function here is going to be from 0 to infinity. And then what is the range of my new function here going to be? Negative infinity to infinity. It's just going to be all real numbers. So make a lot of sense when we actually talk about what these kind of like domains and ranges actually represent. If we've swapped our inputs and our outputs before with our exponential function, what feature of our function were the inputs? What was I actually plugging in when I was plugging stuff in? Yeah, things from the domain, but as far as a feature of my function is concerned, what does x actually represent? Where do I find x in my equation? It's a power. It is an exponent. So with my exponential equations, my inputs were exponents. If I'm taking the inverse function, now what are going to be my exponents? My outputs are going to be exponents, which we kind of see up here, right? We have y in our exponent. That means that our outputs are exponents. This is a super important idea. This is one that we are going to come back to a lot today, is the idea that the outputs that we are seeing for this function are exponents. Very, 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 very crucial. Okay. If the outputs are exponents, then what are we actually going to be plugging into our function? I kind of like to call it the resultants. It's like when we take b and raise it to this output, it's whatever we would get after we kind of do that exponentiation. All right, so I'll call the inputs are the results. It's like the thing that we get after we take a particular base, raise it to a power. For instance, if I wanted to know the output that I would get for plugging, let's say 121 into 11 to the power of whatever my output is, what is the output that I would get for plugging 121 in here? What is the power that when I raise 11 to that power gives me this 121? 2. This would just be y is equal to 2. Let's maybe say that we're looking at 2 to this power of y here. And we'll go ahead and replace x. We'll plug in like a 1/8. Okay. Now, 1/8, having that 8 in the denominator means what about my power? What's going on here? It's going to be a negative power. And then how do I make 2 match up with 8? 2 to the what? 2 to the 3, and so this y is going to be, our output here is going to be -3. So notice we're plugging in the results. Plug in 121, we're plugging in 1/8, and the output, the thing that is getting spat out, is what is the exponent that would give us that result for a particular base. Okay, so that's cool and all. Still a little bit clunky, mostly just clunky in the fact that I don't have it as like y equals. We're kind of having to use some logic to actually write it out as y equals. So we need to kind of have our, not really need, but it would be nice to be able to write this in such a way that our y is solved for, our output is solved for, and also that we're clearly plugging x into some kind of machinery, right? So what we are about to do is a definition. This is not, there isn't logic here. There isn't like a reason why the things line up the way they do. This is purely definitional. We need a way to take our inverse function and solve it for y. And so the way we do that is, instead of writing x is equal to b to the y, which is totally valid, and we will want to occasionally write it as this, we can instead write the exact same statement as y is equal to log base b of x. Okay. Have I changed any of the pieces here? No. They are all exactly the same as what you see with x is equal to b to the y. All right. Our output here represents what? What is y? It's the exponent, so it's still the exponent. What is x? What are we plugging into our function? It's the result. It's what we get when we take a base and raise it to a power. And so the question that this is aiming to answer is, what power do we have to raise b to in order to equal x? All right, so that is the construction that we are working with here. If I plugged in 121 into log base 11 of x, so log base 11 of 121, what power do I have to raise 11 to to equal 121, what is our answer? 2. And so this is an equation that solves for the power that our base needs to be in order to equal something, to equal whatever we're going to plug into. Okay? Purely a definition. I don't want you to get scared or confused by the way it is written as a logarithm. These are equivalent statements. And in fact, when we are defining our logarithmic function, this is how we define a logarithmic function. This is anything y is equal to log base b of x, which is the exact same thing as saying that x is equal to b to the power of y. These are equivalent statements. Right? So there's nothing to really like understand here. This is just a flashcard to learn. It's like the definition of photosynthesis, the definition of a logarithm. All right? It just is what it is. It's how we define. All right. So I want us to be super, super comfortable with being able to switch between these two forms. There are going to be some times where it's really, really useful for us to be in this logarithm form. There are going to be some times where it's really, really useful for us to be in this exponential form. I want us to have enough familiarity to be able to, on a drop, be able to swap between these two forms. All right, so looking at example 1 here. Looking at 1a, got 2 to the power of 6 equals 64. All of these are just true statements. All right, every single one of these is true. 3 cubed is 27. 1/4 to the negative 2 is 16. All right, all of these are just true statements. We are taking these exponential expressions and rewriting them as logarithms. So looking at 1a here, what is my base? What is my exponential base going to be? 2. And so I am looking at log base 2. Okay. What is my result? What am I plugging into my logarithm? 64 is my result. That's what goes into the logarithm. And then what is the exponent that gets spat out at the end of my logarithm? That is 6. Have we changed the content of that statement? No, it's saying the exact same thing. It is saying that if we wanted to know the power that we need to raise 2 to equal 64, that power is 6, which is the exact same thing as saying that 2 raised to the power of 6 is 64. Right? It's just two different sides to approach the exact same statement from. Let's take a look at C as well. Yes, Dylan. 64 is not the exponent. 6 is the exponent.
I'm saying when you put into the new, are you putting 64 into just like putting log base 2 to the 64?
No, log base 2 of 64. So think of whenever I write a logarithm here, the base is kind of telling me the style of logarithm that I'm going to choose. We're going to use the 1970s logarithm that does blah, 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 blah. This is just like the type of machine that we're working with. And then the actual input is the result that we're plugging in, right? So for instance, I would get something different if I plugged in, let's say, log base 4 of 64, right? So 64 isn't our power here, but we're asking kind of a similar question, but our base is different. What power do I have to raise now 4 to equal 64? There is still an answer. This would be 3. 4 to the power of 3 is 64. But the exponent changes, but that's just because we're looking at like a different base. We're looking at like a different machine. I could change it again. Log base 8 of 64, what is this going to be? 8 to what power is equal to 64? 2. 8 squared. All right, so we're plugging in like an end product. It's a little weird. It feels a little backwards, but we're like plugging in an end product and asking what is the exponent that we need to take us to that end product. All right, let's try it again with B is very, very similar to A. Let's try it again with C. What is our base here? 1/4. Okay, so this is log base 1/4. Right? That's just like the type of machine that we're plugging this into. What are we actually plugging in? What is the kind of end result that we see? 16. And what is the power that I have to raise 1/4 to equal 16? -2. Okay. Looking at D, what is our exponential base? P. So this is log base P of, what are we plug? What's our result? W. And what is our exponent? M. Yeah, so think of that base. That's not like a part of our input. That's just like a subscript. It's an index that's telling us what type of machine are we using. In this case, we're using a machine that likes us to be in base 2. We're using a machine that likes us to be in base 11. We're using a machine that likes us to be in base P. Questions here with our definition of a logarithm. What does the output to a logarithm represent? The exponent. What does the output to the logarithm represent? The output, still. I'm asking again, being redundant. It's the exponent, all right? The exponent is the exponent, it's the exponent. What we are looking at, the output, the thing that is being spat out at us, exponent. All right. Now, most of the time, okay, I say most of the time. There's like a slight asterisk on this, which is actually that this isn't true most of the time. For most bases, you indicate the type of base by using this little subscript notation here. So if I want to be in base 2, I say log base 2 with that little subscript. All right. If I wanted to be in base 14, log base 14, log with that little subscript of 14 to tell me what my base is that I am raising to the power of. There are 2 bases that are used so commonly that you just completely forego that notation, right? One of which is used so commonly that it is in fact called the natural logarithm, and its notation is even shorter than kind of just ignoring the base. So 2 types. There is the natural logarithm, and then there is the common logarithm, which I did not include as a definition, but probably should have. So we're going to add it in here, logarithm. Talk about the common logarithm first. This is just log of x without any kind of base indicator. Right? So this isn't to say that there's no base. We're just being told, I'm assuming that you know what that base is. And what is that base that I'm assuming that you know what is? Does anyone know? 10. This is going to be the same as log base 10 of x. There's nothing wrong with writing log base 10 of x. It's just we have a faster way to do it, faster, which is you can just leave off the base. So if I ever ask you what is log of something, base 10, all right? It defaults to base 10. Now, that is until you get to a high enough math class that your professor says, well, the only logarithm that actually matters is the natural logarithm. And so I'm going to continue to write log, and it's not going to be in base 10. It's instead going to be in the other base that we care about, that we use even more predominantly. And that is, again, the natural logarithm described as ln of x. So even shorter than just saying the log of x. And does anyone know what the base is for this? It's that super, super cool number. This is base e. This is log base e of x, where just e is like that 2.71828, blah, 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 blah. All right, it's that number that we got with the continuous modeling for the PERT equation and for various other continuous exponential growth equations. I think it says quite a bit that we call the natural logarithm that has a shorter script, and it's going to be the one that we use pretty much exclusively at upper levels of math, that it ends up being base e. This number is super cool. It's very important. Yeah, Sadie. So we stumbled upon E in a kind of calculus way. It's not the only way to do it. There are some really, really cool kind of resources out there that can lead you to E from like different angles. It keeps showing up like all over. The way we did it was we were looking at that 1 plus 1 over n to the power of n number. And this is technically, okay, to use this in calculus terms, the limit as n approaches infinity. As n gets really, really, really big, this stabilizes to be E. There's a number. It's just like pi as a number. This is like its own special number that comes up over and over and over and over again. And kind of like how pi is related to circles, we could say that E is related to exponential functions. And that would be that's a pretty okay kind of way to liken it. It's like the pi for exponential functions, kind of, which undercuts a lot of the really cool things that you can do with it. But for our purposes, that's good enough. It's like the pi for exponential functions. Yeah.
Did you say yesterday that E to the pi plus pi?
E to the pi, yeah, so E to the pi I is equal to, this is like one of the coolest. It's like when you ask like math teachers like what their favorite equations are, a lot of them will say this is like Euler's equation.
If you can even explain that.
I definitely can, and actually you will be able to explain it by the end of this course. When we look at polar coordinates and complex numbers in polar coordinates. Essentially, pi is a rotation. And if I start at 1 and I rotate by pi radians or 180 degrees, where do I end up? I end up at -1. Yeah. But yes, we'll look at that. We might not look at it in this exact form, but we'll look at like some other ones. Another way to write this is that cosine of pi plus I sine of pi is equal to -1, and that is also a true statement. And this ends up being like equivalent to that. But we don't need to worry about that too much. But that's also, by the way, just the machinery by which you would take like the square root of I is going to be related to that as well, which is kind of cool. And is another thing that we might be able to do. But actually, yeah, we will definitely be able to take the square root. We will take the square root of I by the end of this class. I can guarantee that. So many fun things. And E is kind of at the heart of a lot of them, which is cool. But for our purposes, we just need to know it's a number. It's a little less than 3. It's like pi. We use it a lot for like exponentials. Continuous kind of triggers your thinking. We're going to use E here. All right. So let's take a look at example 2. That was just like a little pit stop because C has some of that trickiness. Looking at example 2 here, we are trying to solve for x kind of extricating x from this, this logarithmic statement, we're going to keep using that definition of our logarithm, but kind of going in the other direction. So this was a lot of taking an exponential statement and rewriting it as a logarithm. Here we are given a logarithmic statement. Let's try rewriting it as an exponential to solve for the contents that we see here. So I have log base 3 of x is equal to 3. How could I rewrite this expression as an exponential statement? Perfect. This is 3 to the power of 3 equal to x. Noticing that this 3 here is our exponent, and this 3 here is our exponential base. And so what is x going to be equal to? 27. Perfect. Right. So again, we've got a lot of utility in kind of being able to swap back and forth between these two forms. Looking at B, log base 1/2 of x is equal to 5. How could I rewrite this as an exponential statement? 1/2 to the power, oh, that's not correct. 1/2, no, I said that wrong. Or I wrote that wrong. You said it right, I wrote it wrong. 1/2 to the power of 5 is equal to x. And so what is x going to be equal to? 1 over 32. When you have a fraction raised to a power, you can raise the numerator to that power and raise the denominator to that power. So 1 to the 5th, or 1 to the power of 5 would just be 1. 2 to the power of 5 would be 32. So 1 over 32. And then ln of x is equal to 7. What is that base there that we assume that we know? That's going to be base e. And so how could I rewrite this as an exponential? E to the 7th is equal to x. And actually, since e is kind of like pi and that it's an irrational number, we are very, very happy to just kind of leave it like this. In fact, I highly, highly, highly encourage you to not plug that into your calculator and round it. That is as accurate a number as you're going to be able to write it as. All right. Any decimal approximation is just going to be less good than e to the 7th. All right. Questions with our logarithm definitions? Okay. I have a question about our logarithm, and this is like the kind of oppositional student question of why on earth are we talking about logarithms? What's the point of logarithms? Why do we care about logarithms? And kind of the broader question there is, why do we care about inverse functions at all? What do inverse functions allow us to do? So something kind of similar to that, or like I think kind of touching on this idea, what was the inverse function of x squared? Yeah, y equals x to the 1/2 or the square root of x. And what happened when I composed an inverse function with its original or vice versa? What happens when I combine them with composition? They cancel each other out. All right. And so why are logarithms going to be really useful for us? They're going to be really useful at canceling out exponential functions. They undo exponential functions in a way that allows us to say, look here, how do I get at that y? Or look over here, how do I get at that x? Now we have the ability to, with logarithms, in particular, those two inverse kind of operations that we said were that f of f inverse of x was equal to x, and that f inverse of f of x was equal to x. Right? If I compose a function in its inverse, the square root of x squared is just x, and the square root of x squared, it's kind of hard to communicate, the square root of x all squared is x, and the square root of x squared is also x. Regardless of how I do this composition, they cancel each other and I end up with just x. Okay, we're We're going to see the exact same thing for logarithms. Note that these are kind of a result of the fact that we are composing inverse functions, but I'm also going to try and present them in such a way that these are just like self-evident, very, very kind of obvious statements that we are making. The first one probably more so than the second one, but hopefully the logic of both is like a very like, okay, this kind of has to be what that is. All right. So the first of these statements is that log base b of b to the power of x is equal to x. Again, kind of composing our function and its inverse. And then the second one is that b to the power of log base b of x is equal to x. Okay, so first and foremost, this is just two inverse functions composed with one another, canceling out and becoming x. So like at a very basic level, this is just what our inverse functions do, is what they're designed to do. But let's actually try and unpackage what each one is saying, because I think when we do, these become like very, very clear. They become a lot more obvious. So looking at this first statement, all right, what do our logarithm functions tell us? What is the output of my log representing? It's the exponent. So this is telling me that the exponent that I have to raise b to in order for it to equal b to the power of x is x. Okay. Well, that's kind of self-evident, right? If I write this as b to the power of x, what power do I have to raise b to in order to equal b to the power of x? Obviously, the answer is going to be it's the power. It's x. All right. Second one, I think, is a little bit trickier to kind of unpackage there. But we can kind of do something similar. Log base b of x, that output, this number, what does this whole thing represent? The output of our logarithm is just even more basic than that. It's an exponent. In particular, it is the exponent that when I raise b to that exponent, what do I get? What is my result? It's the x, right? That's what the x tells us. It's the result of when I raise b to this power, I get x. And what am I doing with that power? We're raising b to it. Right? So this is like b raised to the power that when b is raised to the power, we get x. So again, a little bit of a kind of a mess of the English to untangle there. But really, this here is the power. This is that exponent that when we raise b to it, we get x. And so when I raise b to it, I get x. Again, this idea that our logarithms, that output, represents, just very, very literally represents an exponent, is very, very helpful in kind of unpackaging a lot of what this is trying to say. But this is also just our inverse property. We can also just write this. All right. This gives us a really good tool to actually deal with simplifying logarithms. Our goal, which has kind of been the subconscious goal that you guys have probably had when looking at like problems like 121 is equal to 11 to what power? This kind of subconscious goal is I would like to be able to write whatever my input is in terms of the base that I am being given. So in terms of that logarithmic base, and then the answer to the logarithm is just the power that I would get from that input, right? Which again is like kind of self-evident. It's like, yeah, that's what the logarithm is asking us to do. This is just how we would write it, right? So for instance, in this case, we were trying to use the identity properties to evaluate the following expressions without a calculator. In other words, we are trying to rewrite each of our inputs as a power of the base that we are given. All right. So looking at log base 7 of 343. How can I write 343 as a power of this base, as a power of 7? 7 cubed. Very good. So this is log base 7 of 7 to the power of 3. What power do I have to raise 7 to in order for it to equal 7 to the power of 3? 3. All right. Couple of things that I want to note. First and foremost, I will realistically give you powers that you can probably guess kind of what those powers would be. I like powers of 2 a lot. Probably powers of 2 up to 64 would be kind of good to know. I feel like I could give you those if I'm asking you to do this without a calculator. Powers of 3, maybe up to like 243, I think is 3 to the 5th. Yeah, 243, maybe up to there, but probably more like 81, 27, those kind of powers. Powers of 5, like 125, 625, that'd be like 5 to the 4th, so on. So kind of like smaller powers would be reasonable. But if you needed to figure out what power it is, you can always go to y equals, do that base to the power of x. So let's say, for instance, I wanted to know what power of 7, 343 is. I pull up the table. This should be x. And I look for what is that x value that gives me 434 or 343, and we see that it is 3. So I can rewrite 343 as 7 cubed. Now, notice here it asks you to do it without a calculator. The without a calculator part is really just emphasizing don't just plug log base 7 of 343 into your calculator. That kind of like defeats the entire purpose of the question, which is understanding that this is a power raised to a base using the identity properties. And so like on a quiz like that you guys might hypothetically have on, say, like Tuesday of next week, you would probably not be given a calculator for this. But I would also make it so that the numbers were ones that you either knew, or if you didn't know, I would probably be a little bit more lenient towards helping you kind of piece it together. All right. But for our purposes, we can do y to a particular power and kind of see what that is. So any questions on 3a here? All right. Take a stab. We're going to take 5-10 minutes. Take a stab at B through D. I'm trying to write this as log base b of b to a power so that we can use that kind of identity property in order to really just almost cancel it, but I don't use that of the identity properties. For now, in terms of like the actual evaluating of logarithms, we'll use 1 probably more commonly. I'll show you how to use 2 for changing base. So we'll use this to solve some tricky base change questions, and then we'll use this one for these like just logarithm evaluation problems.
So when you get this 3 right here,
Yeah.
In the base, we use like this here.
Yes, exactly that.
Okay.
So log base 7 of 7 to the power of 3 asks the question, what power do I have to raise 7 to for it to equal 7 cubed? Well, I need to cube it. And so this 3 and that 3 are the same thing.
So like this thing, these two things are the same.
Yeah, exactly. This is like
These sevens are the same.
yeah, pretty much it.
Okay.
Yeah.
So would this be like?
So what's our base if we have log without? So log base and 10. Okay. So 10 to what power? Now, how could I write this as 10 to a power?
And more.
10 to the what is 10,000 going to be? 10 to what power? A quick way to do it for 10 is just count the number of zeros. So 10 to the 4th will be this. So you rewrite this as log implied base 10 of 10 to the 4th. What power do I have to raise 10 to equal 10 to the 4th? 4. Yeah, exactly. Yeah. And then the for C, a lot of people are getting a little bit tripped up by that 2. That 2 just multiplies after you have evaluated the logarithm. So you would first do the log base 1/5 of 625, and then multiply that result by 2. Perfect. Sure. So this would be a lot easier if it were 5, right? Okay. So what power of 5 is 625? Yeah, 5 to the 4. Because 5 squared would be like 25, 5 cubed would be 125, 5 to the 4 would be 625. Okay. And so ideally we would like this to 5 to the 4th, but that doesn't match the basis. How could I match 5 to 1/5? What power would I have to raise 5 to for it to equal negative 4? Exactly. And then you just multiply this by this. Yeah. Yeah. Multiply it again. Or you could do negative 4 times 2 here. I mean, order doesn't matter. No. So this piece is equal to negative 4. 2 times this piece would be equal to negative 4. Yeah. So we're not what? No. Just kind of multiplies them after the fact. Yeah, exactly. Okay, perfect. Okay, so log base ln is log base what? Log base e. So log base e of e to the 2657. So what power do I have to raise e to for it to equal e to the 2657? Exactly. 2650. So yeah. Okay. You multiply. Yeah, so this was negative 4, we're looking at 2 times this. 2 times negative 4. Okay, so I think this one would be a lot easier if it were base 5. Right. So let's try it for base 5 first, and then let's see if we can adjust from base 5 to base 1. Because that adjustment might be easier than like working with the 1 directly. So how could I write 625 as a power of? Okay, well, let's try. So 5 squared is going to be 25. So 25 times 5 would be like 5 cubed. Okay, so that almost gets us there, but not quite. What about 5 to the 4? Okay, so we could rewrite 625 as 5 to the power of 4. And then it's just a matter of how do we match 5 to 1. What could I raise 5 to, or what could I raise 1/5 to in order to equal the other? How do I take a reciprocal of power? flow bus, this would be 1/5. And so since 5 to the 4th is 6.5, and 5 to the negative 1 is 1/5, looking at 5 to the negative 4. Or really it's 1/5 to the negative 4. The other way we can do it is we can go in here and say, okay, let's just go 1/5 to the power of x. Well, we'll take it here. And notice that line x is negative 1. That's what this is. So that was. And we'll look at how we can actually change this base here in a second. Because I think, like, the first step, just rewriting a fractional base as not a fraction, probably makes the whole problem. So perfect. Yeah. So when there's nothing, the implication is 10. So the assumed, the basic, it's called the common logarithm, it's based. Yeah.
Can you just multiply that?
Yeah, so 10,000 is 10 to what power? Not 10 to the 10. 10 to the 10 would be like a 1 with 10 zeros after it. How many zeros? 4. And so that's kind of our cheaty way of just like really quickly getting a power of 10. All right, let's take a look at these. Overall looks really, really good. I do have a comment that we'll make on C because fractional bases are kind of annoying. And actually we have a really cool way to not have to deal with them ever, which I'm kind of excited about, which are cool. And relate to something that we talked about yesterday, which is fun. All right, looking at log of 10,000, what is the implied base when we don't see a base? 10. So this is really like, oh, not friend. All right, we're gonna die on me now. Okay. So this is really like log base 10 of, and then how could I write 10,000 as a power of 10? 10 to the 4th, I like. This is going to be 10 to the 4th. What's kind of our really fast way of figuring out powers of 10? Just count the number of zeros and that'll tell you the power of 10 that you're looking at. So in this case, we've got 4 zeros, 10 to the 4th. And so log base 10 of 10 to the 4th, what power do I have to raise 10 to equal 10 to the 4th? 4. All right. Okay, let's look at C. That 2 we can kind of ignore. That's just going to be multiplied at the end of it. I just threw that in to make the problem more challenging. It doesn't really change the difficulty level. I want to talk about this 1/5 because I think that this problem would be a lot easier if this were in base 5, right? I think the 1/5 just is kind of hard to wrap our minds around. And so if we had a way to take, say, log base 1/5 of some number, we'll say log base 1/5 of x, and turn it into log base 5 of x, then this problem would become a lot more manageable. Is that probably a fair thing to say? It's just easier to deal with 5 to various powers than it is to deal with 1/5 to various powers. So how could we do this? Let's actually take a look here at our good old friend, and this is a spoiler and blah, blah, blah. Okay, so ignore that for now. I want to take a look at what we looked at yesterday, which was this idea of taking a fractional base of an exponent, right? So we compared these two functions yesterday. This was 2 to the power of x, which is our green line here, and then 1/2 to the power of x, which is our purple line here. And what was the observation that we made? What kind of transformation do we see switching from green to purple? A reflection, and specifically, what kind of reflection? Across the y-axis or a horizontal reflection? We have now taken the inverse function, which means our horizontal reflection has also been inverted. What has our horizontal reflection become? What would we predict? If our x's and our y's trade places, then a horizontal reflection should turn into a vertical reflection. It would be reasonable to conclude that we would hope to see a vertical reflection. So in the case of our exponents, 1/2 to the power of x could be written as 2 to the negative x. Notice that 1/2 to the x is the same as making the x negative, making our exponent negative. But now what is our exponent? It's not our input anymore, it's our output. So we're really making our output negative by taking a fractional base. And in fact, we can confirm this. If I compare log base 2 of x to log base 1/2 of x, what kind of reflection do I see here when I compare the blue line versus the green line? This is around the x-axis, but that is a vertical reflection. How do I achieve a vertical reflection? Well, I could have gotten the same result by multiplying log base 2 by -1. This is log base 2 of x. And notice that these lines are exactly the same, right? And so I can rewrite any fraction, any fractional base, as -1 times its reciprocal, times the log base reciprocal, which is kind of cool. It's a nice little trick to kind of have in our back pocket. So if we wanted to make this problem maybe a little bit more digestible, rather than dealing with the base of 1/5, let's actually take this and rewrite it as negative log base 5 of x. This is kind of what understanding our transformations allows us to do. It's just a nice little trick. Now, do you have to do this? No, you don't have to do this. The other way that I would say that we need to approach this, and you can really just approach this with any kind of exponential function, with any kind of logarithm, is to note that our base has our main kind of contributor in the denominator, and it has switched from being in the denominator to being in the numerator. How do I cause that switch to happen? How do I make my fraction flip? I need a negative exponent, and then I can basically just treat this like it's 5. And so this becomes a question of what is 5, log base 5 of 625. And then we, again, take the negative, which is kind of what we're doing with this whole reflection business, but we could do this as well. And how can I write 625 as a power of 5? 5 to the 4th. And so I get that this is equal to -4, but then we multiplied it by 2, and so we got -8. So a little bit tricky when we have those fractional bases, for sure, but we can certainly bypass those now. Now we know a fractional base is the same as the negative version of the reciprocal base. I guess if you wanted to, you could also now turn your base 2s into base 1/2, but like, why would you do that? What kind of monster would do that? And then one last one just to send it off, looking at ln of e to the 2657. ln is what base? Base e. So this is log base e, log base e, do a little e, of e to the 200 or 2,657. What power do I have to raise e to equal e to the 2,657? 2,657. Cool. All right, questions with our logarithms. Kind of how they're defined, how we are evaluating them, anything like that. Yes, no. Yeah. The way that you would do C directly is probably by pulling up the table or some other, thing like that, and writing this as the log base 1/5 of 1/5 to the -4. That's certainly correct. That is certainly correct. I just think coming up with the fact that 625 is equal to 1/5 to the -4 is harder than coming up with the fact that 5 is the same as or that 5 to the 4th is 625. Realistically, they should be similar in terms of difficulty, but I think that extra step of negative to get that flip is actually pretty cognitively tricky. And so we can bypass it by just taking the reciprocal right up front and then multiplying by -1. Just a nice little trick to have in our back pocket. All right. Any other questions here? Alrighty. Cool. We got about a little under 20 minutes, about 20 minutes left. The 3, 1 through 3, 3 for the extra credit tomorrow. Before the start of class, have 8 through 18 finished, I think is the next chunk. It's a little bit more than what we did, but also a lot of the questions are just like, here's an exponential statement, rewrite it as a logarithm. So it shouldn't be too bad in terms of like the length. All right. So yeah, got about between 15 and 20 minutes left. So take a stab at that.